Hello everyone. In this video, we're going to be looking at the density of Q in R. And so we say that the rational numbers are dense in R, and so what that really means is the statement of this theorem, which is to say for all AB, for all AB in R, maybe A not equal to B, which might be a good thing to put here, right? So maybe I'll put A not equal to B. Maybe even more specifically, A is strictly less than B. Then there exists an R in Q such that R is nested between. So what this is really saying is that if I take my real axis and I pick any two elements on the real number line, I'll always be able to find some R, which is, clearly I can find a real number between any of two real numbers. It's always maybe the average of the two. But the claim is that I can find a rational number, which, might not be in the middle, whatever. Might be somewhere to the side or something. But I can find a rational number strictly between A and B. Okay, so, well, yeah, we're going to have to construct this rational number somehow. It's not wildly hard, right? So let's take a look at a proof of this. So, right, maybe want to imagine our real number line here, just to have something to kind of look at. So we're we're also going to be solving the case when A is greater than or equal to 0, the negative cases. It's just an extension, so maybe we'll look at that, but just for the time being, we're going to solve the case when A is greater than or equal to 0. So, we can pick, we have some A here, right? And we have some B. And the first thing is, so I'm trying to find some R in between them, right? So, we could say we need some R equals, maybe we call it M over N, with M in, M is going to be a natural number, right? And N is going to be also a natural number, right? But whatever, we can just call them integers. M, N, in Z, but we're saying it's positive, right? So anyways, integers, M and N, of course, with N not equal to 0, such that M over N is between A and B. And we might rearrange this slightly and say that NA is, M is strictly between NA and NB. Okay, and maybe we'll call that maybe equation 1 or something. So we need to find M and N that satisfy this, right? That's kind of our goal. Find M and N that satisfy this. So we have kind of like two variables here that we can kind of play with. So we might want to fix N, and based off of that, find some M. Okay, so we're going to maybe start by fix N. Okay, and so how, right? Well, what we're going to do is we want our fraction to land in between A and B, right? So we can think of the rational numbers here, right? So if I have like, my numbers, 1 over 2 or something like that, or let's just say M over 2, then I've broken this up into halves, right? Into these increments of a half. So what I want is I want my denominator, so we can maybe write this, right? So we want to fix, well, I said fix N already, fix N, maybe such that the increments of size 1 over N are smaller than B minus A. And what's b minus a? The distance from a to b, right? So the distance from a to b, we want our increments to be smaller than this. So what I mean is to say that I want to fix n such that 1 over n is less than b minus a. And maybe we call n equals n naught such that 1 over n naught is less than b minus a. And we should hold on for a second. And it's like, well, how can I do this? Do I know I can do this? Can I always fix some 1 over n that's less than this? Well, that's a real number, right? The real numbers are closed under addition and inverses. So we have that b minus a is a real number. And so the Archimedean property, right, which I will take as a there's a property of R, right? So I would just say possible by Archimedean property, which essentially states that we can always do this. That as long as I have a real number here, I can always find some n such that 1 over n is less than the real number. Okay, maybe we want to talk about that in another video, but that's the Archimedean property. So okay, so I fixed that. So now my equation, right? My equation 1, like this, can kind of turn into a and not, or and not a, and not b here. Okay, so we now want to fix some m naught, and by fixing it, we want to think about, we want to make sure that this property is satisfied, right? So now we have to think about fixing, too bold, I want to fix m, as an integer. Well, this is kind of how we're going to do it, right? We're going to think about the set A, which is the set of all n in n, such that, or maybe n in n, such that, or maybe we call it m in n, right? Such that m is bigger than a and not. So all the natural numbers, right, that are bigger than a and naught. Well, we know that a is positive, n naught is positive, right? So we know that there exists some natural number that is greater. That's kind of the Archimedean property as well, right? So we might basically what I'm saying is that a is non-empty. It's essentially also the Archimedean property. So also by Archimedean property. A is a set of natural numbers, therefore a has a smallest element. So fix m equals m naught, the smallest element of a. So we have a set of natural numbers, non-empty set of natural numbers. It has the smallest element, so we're going to fix that. Okay, so now we're going to, with this choice of m, we now need to show n naught a less than m naught less than n naught b, right? We need to kind of verify this. Okay, so based on how we picked m naught is the smallest element that is smallest natural number that is still bigger than a n naught. So what that means, right, is we know, maybe we can, I don't know how we want to do this, right? We maybe want to move this down a little bit and say, here we can say that we know that a n naught is less than m naught, but bigger than or equal to m naught minus 1, right? And so we can see from this, okay, because this has to be true because this was, m naught was chosen to be the smallest element such that this holds. So the smaller one must be less. So right there, maybe we call that star, satisfies that, right? So we're already done with that side. And now we just need to show that m naught is less than n naught b. That's what we need to show, right? Well, what we're going to do is we're going to use the other side of this, okay? So we might want to call this 2. So we can say from 2, m naught minus 1 is less than or equal to a n naught. So from this we can get that m naught is less than or equal to a n naught plus 1. Okay, which is what we're trying to show, right? So somehow I want to show that that is strictly less than n b naught. Well, I need to know something. I need to relate a to b. And the way that we've related a to b is by where am I? This expression right here, or maybe this expression right here. Right? That's how I've related a to b. So we can maybe take that, right? We recall. So we know here that we can move a to the, however we want to do it, right? We can move a to the other side. So we can move a to the other side. So we have a is strictly less than b minus 1 over n naught. Okay. So a is smaller. So we make it bigger. If we continue up here, maybe I'll put, dot, 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 right? We make it bigger by putting b minus 1 over n naught times n naught plus 1, which is b n naught minus 1 plus 1, which is b n naught. And so there we have it. We have our conclusion, right? We have that m naught is strictly less than b n naught. It's kind of just like shuffling around some inequalities, right? But we have that, and we also, as I said earlier, we also have that. What am I looking at? Yeah, this side, right? So a n naught is strictly less than m naught. So therefore, we have that the number m naught over n naught is strictly between a and b. And so we've seen how to construct it. Maybe let's look at an example here of this kind of in action. So let's say I have, let's actually find it, So let's say I have the square root of 2 and the square root of 3. Let's say these are my 2 real numbers. And I want to find a rational number that's between them. Okay, well, so the procedure goes like this, right? I want to find some m naught over n naught that is between a and b. So the procedure goes, to find n naught, we think about 1 over root 3 minus root 2, and we find the 1 over n naught, that is, sorry, not 1 over that, sorry, just the difference, b minus a, right? Let me restate this, right? We find n naught such that 1 over n naught is less than b minus a, root 3 minus root 2. And again, this is always possible. So we might just want to do this with a calculator. So maybe I'll just open a calculator here, right? Or maybe I'll do it in Desmos like this. I don't know. Here's the quartic formula that I was looking at. So if I take the square root of 3 minus the square root of 2, I know you can't see this, right? But we have that. So square root of 3 minus square root of 2 is 0.317, blah, 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 right? And let's find the first natural number that's less than this. So like 1 over 2, 3, still bigger, 1 over 4, right? That'd probably be the first one, 0.25. So that means we fix n naught to equal 4. Now for m naught, we think about the set of all m in n such that a n naught is less than m. So what does that mean exactly? Well, a is root 2, n naught is 4. So 4 root 2 is less than m. So all the natural numbers that are bigger than 4 root 2. Again, we're going to just do some numerical approximations here, right? So 4 root 2 is 5.65, whatever. So the first natural number that is bigger is 6. So we fix m naught, right? So this is approximately, 5.8, whatever. And so we fix m naught to be 6. So the claim is that 6 over 4 is strictly between root 2 and root 3. And, right, we can maybe find some approximation. So this is like, around 1.4. Right, so, just to, around 1.4. And then root 3 is around 1.7. And in fact, 6 over 4, right, which is exactly 1.5, is between these two rational numbers, irrational numbers. And there you have it. Hopefully that example kind of locked in the procedure there, right? So the proof here is that we can do that always, right? But technically we can do it always if a is positive. Okay, that's all for this video. Thanks so much for watching. Hope you enjoyed. There's the theorem we proved.